they make lactate instead. They do anaerobic metabolism. They don't get as much energy out of it, but the reason they do is because they don't have enough oxygen. So you can look at lactate. If somebody has an elevated lactate, that's a sign of inadequate delivery for what consumption they need. The other thing you could look at is central venous oxygen, right? And the reason you look at central venous oxygen, again, usually hemoglobin molecule goes by, the organism takes off just a little bit of the oxygen, most of it's left on, and when you look at the oxygen concentration in the right ventricle or in the central veins, it's lower than it was arterially, but not much lower. Right? Usually we look at, somewhere between 70 and 75 is probably a normal central venous oxygen for somebody who's not stressed, somebody who's not really, taking off a lot of oxygen. You can see it much lower than that in shock states because the organism says cardiac output is lower, so I have to harvest more oxygen as it goes by. So then the oxygen that you see in the central veins will be lower. Okay? So what is this? This is a normal state, right? Again, 100% sat. It's used in the tissues and it comes back to the venous side relatively saturated with oxygen, right? So, and what will tell you about, or what this tells you about what's going on, so there are different things you could get. The SCVO2 can be different. It can be high, can be low, can be about, can be what you'd expect, right? So what does a low SCVO2 mean?
The body's harboring more oxygen.
So it means that the body is sort of harvesting more oxygen than normal. Okay? So an analogy I always give is, let's say you're a chef in a restaurant, okay? And you have a conveyor belt that just takes the food out, or takes the conveyor belt, you put the plates on the conveyor belt and the conveyor belt goes out and people take what they want, and then it comes back to the other side and you get to see before the plates get empty how much food's on the plates, right? So if you're a chef and you put plates down and the plates that are coming back on the other side are filled with food, what does that tell you? What is it? Okay, it tells you, A, the food is bad.
Don't like your food.
Okay, what else could it tell you? It means that
they're not eating.
Nobody's eating because they're not hungry, or there's way too much food, right? Or it means that there's nobody there. Okay? If you send out plates and the plates come back and they're empty, right? That means the food is good, right? But it also means that you may not be sending out enough food, right? Right? If you send out a plate and every plate comes back empty, that means that they're consuming everything that you send out. So maybe you need to send out more food,
portions,
or bigger portions, or what have you. Okay? So it's the same thing with hemoglobin. So a hemoglobin molecule that goes out 100% sat and comes back 50% saturated, much lower than you'd expect. That means that either consumption is up, or it's not being delivered fast enough. Right? The conveyor belt is too low. The cardiac output is low. Right? So low SCVO2 is usually associated with situations where cardiac output is low. Or it may also be maybe the arterial sat was only 80% and it comes back at 50, but that's because it's still taking off the same amount of oxygen. It's just not you just weren't sending out, it wasn't concentrated enough in the beginning, right? So it just means usually that either cardiac output is low or hemoglobin is low. You're just not providing it. Okay? And oxygen consumption is more. What does a normal SCVO2 mean? Well, normal SCVO2 could mean that you're doing what you need to do.
Okay.
Or it could mean that, you know what, the organism is having difficulty taking the oxygen that you're sending out for one reason or another, right? And classically, in sepsis, right, one of the things we see in sepsis is that central venous oxygen is higher than you would expect it. And the reason is because the cells cannot harvest the oxygen normally. They can't use it. The mitochondria, so the actual portion, the organelle in your cell that takes oxygen and glucose and makes energy, is poisoned. And we've proven this, like taking serum from people, or taking serum, white cells from people who are septic, and then looking at how those cells actually use oxygen. We've shown that, somebody's shown that the mitochondria are actually poisoned. So they can't, even if the oxygen is there, they can't use it. So it just goes back in the circulation. The other thing in sepsis is that those precapillary sphincters shut, and blood just gets shunted by the tissues. So it's higher than you would normally expect it. Okay? So lactate, which we talked about, is a product of anaerobic metabolism in the setting of cellular hypoxia, right? There are only really 3 reasons why you'd ever see a high lactate. Either because there's anaerobic metabolism going on, certain drugs can cause lactic acidemia, and the drug that I can think of most commonly is metformin, which we don't necessarily deal with a whole lot in here. And then the other one I can think of is hepatic dysfunction, because the way that your body gets rid of lactate is through something called the Cori cycle. It takes lactate and it turns it into something else. So, and the 2 most common reasons we see lactic acidemia are hepatic dysfunction and inadequate oxygen supply, and almost all of our patients it's because of inadequate oxygen supply, because there's anaerobic metabolism going on in the organism. And as this graph clearly shows, mortality goes up as lactate goes up. And that makes sense. The more anaerobic metabolism you're engaging in, the less effective you are at supplying enough oxygen. And when cells don't get enough oxygen, eventually the cells die. And if enough cells die, then tissues die. And if tissues die, then organs die. And if organs die, then people die. All right, so same lady. So what do we see? She has a blood gas of 7.32, 32, 68. And she has this set of electric lights. Right? So sort of changing gears here, does the acid-base status suggest the patient is seriously ill? So, how do we know about somebody's acid-base status? What 2 pieces of information are essential to look at in the ABG?
The pH.
pH
Yeah.
and the PaCO2, right?
Yeah.
So we know that the pH is 7.32, which is low, which is lower than normal. Usual pH is 7.35 to 7.4. Right? And we know that PaCO2 is also low.
Yeah.
Okay? So, when we look at an ABG or acid-base status, we look at a few different things. We look to see if we think the patient is acidemic or alkalemic. So, pH is less than 7.35 or greater than 7.45. Do we think it's due to a metabolic problem or a respiratory problem? We'll talk about that in a minute. Is it acute or chronic? And then is respiratory compensation enough? And then we're always going to calculate an anion gap, not from the ABG, from the electric lights, right? So in this case, is the patient acidemic or alkalemic? So the pH is 7.32, so that is acidemia. That's right. Right? Is it respiratory or metabolic? So remember, normal PaCO2 is about 40. Probably 35 to 40, 35 to 42 or something like that. As PaCO2 goes up, your pH will go down. So hypoventilation will cause acidemia. Hyperventilation will cause alkalemia, right? So it'll cause you to become more basic, more alkaline. So if her PaCO2 is 32, so that's low, right? So you would expect her to have, if the respiratory were the primary process, you'd expect her to be alkalemic, and she's not. She's acidemic, right? So it's probably not a respiratory problem, it's probably metabolic, and her respiratory system is trying to compensate. Okay? Then is there adequate respiratory compensation? So in order to figure that out, you take the PaCO2 and you take the serum CO2, which in her case is 16. You multiply it by 1.5, and that makes it 24. And then you add between 6 and 10, something between 6 and 10. So I usually just add 8, and I just see what does that look like. In her case, it's 24 plus 8 is 32, so it's probably adequate respiratory compensation. And one thing you'll hear me say hundreds of times, you really can't compensate back to a normal pH. So if you're adequately compensated, the pH is usually 7.32, 7.33. It's not usually normal. If the pH is normal, right, with an abnormal CO2, now you've got another problem. Now you've got, not only do you have metabolic acidosis, but you've also got too much. You're actually blowing off too much carbon dioxide. Your PaCO2 your pH should not be normal. Right, so this compensation is probably good enough. Okay? So what's our anion gap? So the anion gap is, so what are anions, right? Anions are, so an anion is a negative ion, right? So the anions are chloride and bicarb. Okay? In order to figure out the bicarb, you subtract the anions from the cation. Now the potassium is always about 4, so you don't actually include potassium. So it's just sodium minus chloride plus bicarb, right? So is there an anion gap? Or how do you calculate it? So that's how you calculate it. So in this case, the anion gap is 142 minus 122. So the anion gap is 20. So the truth is there's always an anion gap, right? And what accounts for the anion gap? What negatively charged things are floating around in your body because you can't be positive or negative, you always have to be neutral, right? So your charge is neutral, you know, right? So you think you're a Republican or Democrat, you're actually always neutral, you know, right? But in this case, the thing that accounts for that anion gap is proteins, and in particular, albumin is the one that accounts for most of your anion gap. So if you have a normal albumin, your anion gap normally is probably somewhere about 12, okay? But as your albumin decreases, right? Like normal albumin should be around what, 3 or 4? You drop your the normal anion gap will drop by about 2.5 or 3. Okay? So in this case, the anion gap is, do we know the albumin?
No.
They're implying that, oh, because it's 2. I'm sorry, we were told it's 2, right? So normal anion gap is about 12, right? So since albumin is 2, so that's 2 down from what it normally is, it's only around 4. Then it's about, that means this patient's anion gap should be only about 6. So she has a very large anion gap at 20, very abnormal. Okay? So she's intubated because she got worse. A-line's inserted, she has a central venous catheter. The central venous oxygen is 60, which is much less than you'd expect, and the lactate is 6. So do we think we're delivering enough oxygen? This is awesome. It's like, people, okay. Why do we think we're not delivering enough oxygen?
Lactate is still high.
So she has,
Blood pressure is low.
unless her liver's not working, or she's metformin toxicity, probably chances are that we're not delivering enough oxygen for one reason or another, right? Does the CVP tell you you need more fluid? Well, the answer is, I don't really know, right? Because what's the CVP that you need to get a normal cardiac output is different than the CVP that I might need to have a normal cardiac output, right? And your guys' hearts is probably a little bit more flexible, a little bit more pliable than mine is, right? Because I'm older than all you guys. So, therefore...
Stop and restart.
It's 12 minutes.
Yeah, 15.
Are we okay?
Yeah.
Okay. So the answer is I can't really tell you, right? But I do know that I'm not delivering enough oxygen for one reason or another. So we're gonna have to do something about it. Okay? What else can you check to see if a patient should get fluid or not get fluid? Well, you can do a couple things. You can, in mechanically ventilated patients, you'll see us look at the A-line tracing, right? And Ronnie and I will stand at the foot of the bed, and I'll say to the resident, oh, Brittany, do you think the patient needs more fluid? And the resident will be like, oh, I don't know, Jace, you know, the urine output's kind of, and I guess. But if you look at the A-line, right? Every systolic hump on the A-line should be about the same height. And if that's variable, especially when they're mechanically ventilated, when they have positive pressure ventilation, right? So let's talk about how the heart fills. So the heart fills just passively, right? It's just like filling up your sink. You just open the spigot, and the pressure in the spigot is higher than the pressure in the sink, so the water just flows in, right? There's no pump. You don't have to do anything to make it. So the pressure is higher here than it is here.
Your attention, please. Dr. Firestone. 8th floor, room 803. North building, 8th floor, 803, Dr. Firestone.
Right. So you guys just be careful, okay? Right. So, and your heart feels the same way, right? So the right ventricle or the right atrium just fills with blood because central venous pressure is higher than the pressure in your chest, in the thorax, in that place. The problem when you're on mechanical ventilator, right? When you push air into the chest, the pressure inside the thoracic cavity goes up. So it will decrease filling if you're even a little bit hypovolemic. And what you'll see that the height of that systolic blood pressure will be variable. When the patient is given a breath, the systolic pressure will drop a little bit, and then when the breath is over, the pressure will come back. And that you'll hear us say, there's respiratory variation on the A-line. Oh, look, you can see the respiratory variation in the A-line. That means the patient probably could use some fluid. Because if you're euvolemic or a little bit hypervolemic, then you won't see that, right? And Do they have an example of it? Yeah, they have.